I will look at Bayes' rule again and make an observation that is really non-trivial. Here is Bayes' rule, and in practice, what we find is this term here is relatively easy to compute. It's just a product, whereas this term is really hard to compute. However, this term over here does not depend on what we assume for variable a. It's just a function of b. So suppose for a moment we also care about the complementary event of not a given b, for which Bayes' rule unfolds as follows. Then we find that the normalizer p of b is identical whether we assume a on the left side or not a on the left side. We also know from prior work that p of a given b plus p of not a given b must be 1, because these are two complementary events. That allows us to compute Bayes' rule very differently by basically ignoring the normalizer. So here's how it goes. We compute p of a given b, and I'm going to call this prime because it's not a real probability, to be just p of b given a times p of a, which is the normalizer, so the denominator of the expression over here. We do the same thing with not a. So in both cases, we compute the posterior probability non-normalized by omitting the normalizer b. And then we can recover the original probabilities by normalizing based on those values over here. So the probability of a given b, the actual probability, is a normalizer eta times this non-normalized term over here. The same is true for the negation of a over here. And eta is just the normalizer that results by adding these two values over here together, as shown over here, and dividing them for 1. So take a look at this for a moment. What we've done is we deferred the calculation of the normalizer over here by computing pseudo-probabilities that are non-normalized. This made the calculation much easier. When we're done with everything, we just folded it back in the normalizer based on the resulting pseudo-probabilities and got the correct answer. The reason why I gave you all this is because I wanted to apply it now to a slightly more complicated problem, which is the two-test cancer example. In this example, we again might have our unobservable cancer C, but now we're running two tests, test 1 and test 2. As before, the prior probability of cancer is 0.01. The probability of receiving a positive test result for either test is 0.9. Probability of getting a negative result, given them cancer-free, is 0.8. And from those, we were able to compute all the other probabilities, as I'm just going to write them down over here. So take a moment to just verify those. Now let's assume both of my tests come back positive. So T1 equals plus and T2 equals plus. What's the probability of cancer now? Written in short form, probability of C given plus plus. I want you to tell me what that is. And this is a non-trivial question. So the correct answer is 0.1698 approximately. And to compute this, I use the trick I've shown you before. Let me write down the running count for cancer and for not cancer as I integrate the various multiplications in Bayes' rule. My prior for cancer was 0.01 and for non-cancer was 0.99. Then I get my first plus, and the probability of a plus given that it's cancer is 0.9, and the same for non-cancer is 0.2. So according to the non-normalized Bayes rule, I now multiply these two things together to get my non-normalized probability of having cancer given a plus. Since multiplication is cumulative, I can do the same thing again with my second test result, 0.9 and 0.2, and I multiply all of these three things together to get my non-normalized probability P prime to be the following. 0.0081 if you multiply those things together, and 0.0396 if you multiply these guys together. And these are not a probability. If we add those for the two complementary event cancer and non-cancer, I get 0.0477. However, if I now divide, that is, I normalize those non-normalized probabilities over here by this factor over here, I actually get the correct posterior probability, P of cancer given plus plus. And they look as follows: approximately 0.1698 and approximately 0.8301.